Hello everyone, I'm Runzhao Yang from Tsinghua University. I'm excited to present our work TINC, Tree-Structured Implicit Neural Compression. Implicit Neural Representation, INR, is emerging as a promising data compression technique. However, limited spectrum coverage is intrinsic to INR. Preliminary studies can only exploit either global or local correlation in the target data, and thus of limited performance. In this paper, we propose TINC to conduct compact representation for local regions and extract the shared features of these local representations in a hierarchical manner. Extensive experiments show that TINC outperforms the SOTAs on the high compression ratios. Biomedical imaging is visualization of organisms at different scales of cells, tissues, and organs using various imaging techniques. Biomedical imaging data with high sampling rate, high imaging speed, high dimensionality, and large volume. Therefore, a high compression rate compression method needs to be proposed to reduce storage and transmission costs and improve analysis efficiency. This brings the challenge: how to design a high compression rate biomedical imaging data compressor. Implicit neural representation (NR) can describe the target scenes with high fidelity using a small number of parameters, and is emerging as a promising data compression technique. However, NR is limited confronted with large-size data. NR is intrinsically of limited spectrum coverage and cannot envelope the spectrum of the target data. Two pioneering work using NR for data compression, including NERV and ICI, have attempted to handle this issue in their respective ways. NERV introduces the convolution operation into NR. NERV reduces the required number of parameters using the weight sharing mechanism. However, convolution is spatially invariant and thus limits NERV's representation accuracy on convex data with the spatial varying feature distribution. On the other hand, ICI adopts divide and conquer strategy and partitions the data into blocks within NR's concentrated spectrum envelope. ICI improves the local fidelity, but ICI cannot remove non-local reductions for higher compression ratio and tend to cause blocking artifacts. In this paper, we introduce TINC, Tree-Structured Implicit Neural Compression, where we propose to build a tree-structured multi-layer perceptions, which consists of a set of NRs to represent local regions in a compact manner and organizes them under a hierarchical architecture for parameter sharing and higher compression ratio. First, we borrow the idea of ensemble learning to partition the target volume into blocks and use multiple loss expressive FK to achieve a powerful representation. We adopt the divide and conquer strategy to assemble all implicit functions that represents data at its corresponding coordinate region. Then, we let these FK share their neural network parameters hierarchically with each other according to the spatial distance between corresponding regions. For the leaf node at level L, it is corresponding MLP implanted hidden layers can be divided into L segments. And the sharing mechanism is defined on the octal structures. For example, if Fi and Fj share the same ancestor nodes at 1 to 3 levels, 3 pairs of hidden layer segments will share the same parameters. Finally, we introduced the tree-structured MLP based on the L-level octal partitioning. Each node contains a hyperlayer consisting of some fully connected layers and takes the output of this parent node's hyperlayer as input. Root node and leaf nodes additionally contain the input and output layers respectively. The output information of the leaf node is processed by the hyperlayer in its ancestor nodes. At the same level, all sibling nodes share the same parent node, and thus take the same information as input. To evaluate our approach, we compare TINC with SOTAS on massive biomedical data. As we can see, our method outperforms SOTAS under high compression ratios. Some visual comparisons of the compressed data slices are displayed in this figure. We outperform SOTAS and avoid blocking artifacts at the boundary. We also analyze TINC's flexibility to different cases via experimentally studying the effect of 3 case settings: number of tree levels, intra-level parameter location, and inter-level parameter location. For the limitations and future extensions of our work, similar to all current LNR-based compression methods, TINC is of high decompression speed but slow in compression. Since it takes the time to pursue the MLPs matching the target data. So we plan to combine meta-learning to find the best initialization parameters for each organ to speed up TINC.